Hi, everyone. It's a bit challenging to give a talk after Google because the bar is really high, but we'll try. So WebRTC is a great platform that provides tons of features, but for those of us whose paths are somewhat diverging, life can be very challenging. So hopefully today we'll talk about some helpful process that we discovered in order to optimize the encoders to squeeze every bit of performance out of it for video streaming. So for those of us who are not familiar with what we're doing, as Tsahi said, so we're using video streaming to drive cars remotely. Actually, we're not doing it ourselves mostly. We're providing autonomous vehicles companies with a software development kit that allows them to remotely control, monitor autonomous vehicles. And those vehicles can be anything from a delivery robot, a yard truck, big trucks, cars, forklifts, anything. And we're doing this using the public cellular network infrastructure. So yes, some of you are laughing because for those of you who don't think that real-time video streaming is hard enough, our problem space is even more interesting. So first of all, we're dealing with highly variable network bandwidth, and some of the problems that everyone here is well familiar with, such as the bandwidth bottlenecks and how they affect the video, and data transfer obviously is even more critical for us. So here, chart on the right shows on the bottom the RSRP, basically the measurement of the signal strength from a cell tower, and you can see how when it drops, we have an immediate decrease in bandwidth, the yellow chart. And we're going from about 5 megabits upload from the vehicle to sub 1 megabit upload in a matter of a few seconds. So if the bandwidth, bitrate management, congestion control is not done properly, we immediately see a huge spike in latency, which is obviously a huge risk factor for remote driving. The second challenge we're dealing with is that the videos that we are capturing are highly dynamic. So unlike the conferencing space where we have mostly talking heads on static backgrounds, we have multiple cameras that are all having dynamic images facing forward, backwards, sideways, and that obviously creates another challenge for a video encoder. Then our customers obviously requiring very high performance from us, so latency, frame rate, and detail are all very important factors, actually in pretty much this order of priority. And then the available resources that we have on vehicles are often limited because often we have to deploy on a very small vehicle, the size of a chair if it's a delivery robot. And we have to run on very small devices with very small power consumption. So that limits type of software that we can run there. And to make things worse, not only that, but also we cannot standardize hardware because the AV industry is not very mature. And many companies are creating their own hardware platforms or they're picking the vendor of their choice. There is no common hardware stack, so we have to fit whatever the client's asking us. So it becomes pretty clear that running a high-performance video codec is one of the key ingredients to successful teleoperation. And one of the key things that we need from the encoder is the ability to adjust bitrate in real time, mostly multiple times a second, and also have a very wide range for that bitrate control. So we can be running encoder at super low profile, 50 kilobits a second in extremely low network conditions, and then going up to multiple megabits a second when the conditions allow us to do so. And then hardware acceleration is something that is sporadically available to us based on the hardware, so we have to also fit into that. So given that encoder is very important, and it's actually hard to fit it sometimes into given hardware, the biggest challenge becomes how do we optimize the performance of the encoder. So if we're running something like a WebRTC out of the box, we get really nice VP8, VP9 encoder that's tightly coupled with WebRTC itself. We have good congestion control, and things work well without a lot of fine-tuning. But if you diverge from that path, if you're trying to use another encoder, then the challenge of how you get the best performance becomes pretty apparent. So on this chart, you see just a scatter plot of multiple encoding profiles ran at different bit rates. And you can see that for every bit rate on this scale, you can end up with vastly different quality scores. And I'm going to cover how we actually calculating the quality there. But the challenge is that depending on how you configure the parameters for the encoder, which many of them having many knobs, you can end up with vastly different performance. So our goal here, when we started working with encoder, is to maximize the quality for every bitrate level that we need from the encoder. And we came up with a very simple 4-step framework. So first thing, we identify which knobs does the encoder have. So in case of H.264, this is a list of the main parameters that you would typically tune. Then we're generating a large grid map of all of these parameters in hundreds or thousands of combinations. And then we are running a encoding with the encoder of choice with a full grid map and measuring the bitrate and quality. And finally, we're trying to construct the curve of the best parameters, the parameter curve that we should operate our encoder on. So a little bit about quality. So we decided to adopt this framework called VMAF, developed by Netflix. It's a framework that allows to tie the output of the encoder to the actual human perception. So the way it works is that they use multiple low-level metrics such as PSNR, SSIM, etc., as features to train a model that uses the data set labeled by actual humans to predict how would a human react to a video and how distorted the human would believe the encoded video to be versus the original. And one of the reasons why we decided to use that framework is because it allows to train your data set in the domain of choice. And for us, we believe that the perception of the video and the things you care about and the quality of the video are different when you're trying to drive a car at 30 miles an hour versus when you're watching a TV show on your sofa. And I would like to walk through that process for tuning the encoder on an example of H.264. The reason why we chose H.264 is because we had a customer that needed us to run on a very small device, so the NVIDIA Jetson Nano, because of the space and power constraints on their vehicle. We also needed to have browser support on another end because the UI for the remote operator was built in the browser. And one interesting thing about that configuration is that you cannot run a proper software encoder on this device if you're trying to encode for high-quality video streams. So you have to use hardware acceleration. And H.264 tend to have a pretty mature hardware acceleration implementation on that particular device. And so putting our, oh, that's nice G there. Putting our encoder back into play, we took a video, raw video captured from one of our vehicles, and then we encoded it using a software implementation H.264 on the CPU and hardware implementation on NVIDIA Jetson Xavier. And then we scored every video with VMAF. And we ran about 2,400 profiles for that video. And then the next step is doing analysis of that. So one of the things that we decided to start with is understanding how sensitive is the quality and bitrate to the choice of iframe interval. And in general, it is believed that you should choose iframe to be as rare as possible because it's heavy. However, in our world, because we're dealing with highly variable network conditions, it could be not very wise to set the iframe interval to be too rare, because if we have a packet loss and iframe ends up corrupted, you can have artifacts for multiple seconds, which is very bad. So what we found is that for the entire range of our parameter space, the iframes don't have very high impact on the bitrate and quality, relatively speaking. But that's if you look at the entire range of the parameter space. If you narrow down to the actual bitrates that you would want to use, then the sensitivity is about 20–30%. So depending on how you choose the iframe interval, you can save 20 to 30% of bitrate, which is actually fairly significant. And what we actually decided to do for our use case is use high iframe intervals for low resolutions when we know that network is prone to have higher packet loss, because we run low resolutions at low bitrates, obviously. And when we scale up to higher resolutions, we can make iframe less frequent. And then this is one of the more interesting curves. So it shows you the relationship between bitrate and the VMAF score for both hardware and software codec implementations. So first thing, we obviously notice the logarithmic relationship between bitrate and quality. And by the way, all these profiles are just for one resolution. In this case, it's 320p at 16 to 9 aspect ratio. So at some point, we clearly see that the encoder maxes out its abilities to give you better quality as you give it more bitrate. So another thing you see is that the software implementation is much more efficient at the low bitrate, so below 0.5 megabits. And then hardware implementation becomes slightly more performant as you go to higher bitrates. And the same story largely holds true for high resolution, so 720p here. And we also notice another interesting thing. Hardware encoder abruptly ends at about 1.5 megabits, and it's not because we didn't try. It's because the encoder is not capable of giving you lower bit rates, even if you try to push it that way. So no matter how hard you try, it will always give you 1.5 and more at 720p. So that is a very important limitation of the encoder to understand, because that means that it changes the way that we would control it. And from the previous chart, from this chart, we see that software encoder tends to be more efficient at lower bit rates, but what is interesting to see is how efficient if you consider the entire range of resolution space. So we decided to construct this graph, which actually shows you how much performant the software encoder is over hardware encoder. And you can see that at lower bit rates, again, below 0.5 megabits, the performance difference is very high. So you can get 3-4x more better quality for a given bitrate if you're running a software implementation of H.264. However, as you bring up the bitrate higher, the difference becomes smaller and smaller. And then on very high bitrates, hardware encoder becomes a little bit better than the software. And then finally, we already saw that all the bitrate quality curves are logarithmic, right? So an interesting question is, how do you control encoder such that you don't end up on a suboptimal curve, right? You don't want to stay somewhere here where you don't scale the quality up even if you increase the bitrate. So what is important here is to construct some sort of an envelope curve that allows you to pick the best possible trade-off between the quality and bitrate. And you can do this by generating a family of curves for all resolution levels, and then finding the one which gives you basically the Pareto optimal curve. It is worth mentioning that this case, this particular results are true on average for a video of 45 seconds long captured in a particular camera in particular light conditions. So if we have to be serious about using the codec at maximum performance levels, we actually have to construct these curves for different conditions, because they likely would be somewhat different. So all in all, we've seen that codec has a huge impact, obviously, on the quality of video streaming, and that picking the profile setting for the codec and tuning all the knobs in the right way has can have an extremely big impact on your performance, especially if you're not running highly optimized solutions such as WebRTC's VP8. And also, hope you found our simple 4-step framework interesting and useful. For us, the next steps would be, 1, adopt the VMAF and train it for our videos and get the real feedback from teleoperators, as well as do the same kind of profiling for other codecs. And by the way, we're hiring. If you're interested about teleoperation, find me after that. Thank you.
Thank you.